Ladies, gentlemen, we are taking off. Today, good morning. Okay, hope this is a good way to wake you up. So the bullets, number 1, number 2, number 3 are the usual ones. Know that number 3, we do have one more quiz today because I decided to slip in one more today. Because it's a very important part about HTTP. Polly felt that I need to stress that part. Morning, Yin-Yo. Tony, who are you? Probably one of the students auditing the class. Welcome. But if you are one of the students registering for the course, definitely let me know. You definitely draw my attention. Okay, Tony, let me know in case you are one of the official students in the class. Now, bullet number 4 here says, ep8.go, the grades are out. There is a few words of caution from Polly, so please go to the ep8 channel to find out. ep3.go will be due next Saturday, so you might want to start early because in ep3.go, you will be using the new Socket API we just talked about yesterday, but we'll be using the Socket API from Golan. So it's all new for you guys. You might want to start early. And Polly also sent a gift to all of you. Okay, each team, it's a special file called gift from poly.txt because PA3 is about writing the client side of a file upload service. Okay, so file upload service is part of the file transfer protocol, in fact. But we are not following the FTP protocol. We are creating our own and simplified. So that client will be uploading a file to the FTP server that Polly has already set up. Okay. Now, to avoid confusion, please upload the gift from poly.txt file. If you log into your team account, you should see from your home directory such a file. The detail is in the PA3 channel. Okay, so every now and then, Polly might have something to communicate to you guys. And in case you guys have questions specific to the PA, definitely post them there. Okay, the reason that the PA seems to be an independent set, during the live sessions, we don't teach Golan programming, but you see that Polly has a series of videos as well to accompany the PDF descriptions. So in case you run into trouble reading the descriptions, watch the videos and you can do it 2 times speed up. They'll go really fast. Okay. So instead of struggling to find out exactly what syntax to use, maybe watch the videos. It might give you some inspirations. And now let's go to the topics today. Yeah, we need to still finish up section 2.1. There's one more QoS requirement called security and how we have another transport layer service protocol there to support security. The first video is just an overview, and the second video will talk a little bit more about the detail. All right, security CP. This is the next topic. Yeah, if you recall, when we were talking about these service requirements, right, there are 4 of them. Reliability, which is supported by the TCP. Delay requirement, right, it's somewhat supported by using UDP. Bandwidth requirement, and that might be better supported by UDP, but TCP might do a reasonable job. But the 4th, security. Yeah, the fact is that TCP and UDP, none of them provide security. There's no encryption at all. If we send passwords through the internet straight using TCP or UDP, it's essentially clear text. If there's someone intercepting the message, and that someone gets access to our bank accounts or gets into our Amazon.com's account. So none of these cases is good. Big money loss potentially involved. So demand is growing, therefore there is need of these secure layers. So this is secure socket layer. So what it means is that before messages go through the socket and go out on the internet, let's make sure that it's secure. Okay, so it's to provide encryption to messages that's going into a TCP socket. As a result, then we can encrypt messages using a key, or we could verify the receiver using a certificate. Okay. So this is just as important as trying to make sure that the data is confidential. Okay, because how do you know if this server that you are contacting to is indeed a Google server, right? How do you know if it's indeed your bank's server? So this is to identify whether the person you're talking to is indeed the person you're expecting. This is just to make sure that no one can understand the message. No third person can understand the message. Okay. And SSL is at application layer. Yeah, it's on top of TCP, therefore it falls in the application layer. But it's also right underneath the application layer protocol, so message go through the application layer protocol, and then to the SSL, and then to TCP. Okay, so this picture below illustrates what I meant here. So SSL right here, right underneath the application layer protocol, but right above the transport layer protocol. Last, SSL socket API. Yeah. To implement SSL, there are APIs available for each programming languages. In Chapter A, you will see Python's API to try to encrypt messages before they send messages out onto TCP socket. Now, in this semester, towards the end, one of the PAs, you will also be exercising the APIs in Golang to do secure TCP. But there we'll be using this TLS, Transport Layer Security Support. Yeah, this is actually a newer term for SSL. So nowadays people don't call the security support over TCP SSL. They are all referred to as the TLS. Okay. If you think about it, this makes a lot of sense because, hey, SSL there is not really a layer. It's more a support for security. All right. So let's take a look into how TLS works. Okay, the protocol and how the messages are being exchanged. Next, let's explain how TLS works. Before that, let me go back to the very fundamental computer security. How do you encrypt a message such that it can be kept as a secret? So the classic approach is the secret key mechanism. So what we do there is to generate a key, and we share the key with Bob and Alice. So when Alice has a message to send, use that key K, apply the encryption function, and it's going to generate something that's messy. So a third party in the middle here might intercept the message, but without knowing the key, it's not able to decrypt it. Bob, on the other hand, receiving the messy message, using the key, can restore the original message. Okay, so this is the classic secret key communication. Unfortunately, the secret key system will not work to implement TLS. If you think about it, we have one shared secret key. Let's say if Alice is the one generating the secret key, Alice is yet to send the secret key to Bob, isn't it? I mean, didn't we need TLS because we fear we send password in clear text to the other end? So Alice here is sending the shared secret key in clear text to Bob. Same problem. Yeah, so we do have a bootstrap problem with the secret key. Now, to address that problem, we use this other system on top of secret key. It's called the public key system. So instead of using one shared key, public key system generates a key pair. One is called the private key, the other is called the public key. All right, so the receiver of the secret message is over here. Sender of the secret message is on the other side. What the sender does is to plug the message she wants to send, and then encrypt it with the receiver's public key. Yeah, the reason that it's called the public key is exactly because R is going to give out that key to the public, including the sender here. So this is going to scramble the origin. So this function is essentially scrambling the original bits here using this particular parameter. So the encrypted message, as it arrives at the receiver there, then apply the same function and take the received message, and receiver can decrypt with the other key in the key pair. So this is going to give the original message back. Now, the private key is the one kept by the receiver, and no one else in the world will know. Therefore, you ensure that no one else will be able to decrypt the encrypted message. So only the receiver can see the original message. So this is how the public key ensure secret exchange. So TLS illustrated up here works this way. Alice here is a client requesting service from Bob here, a server. So client here first sends hello message to the server. Server in response sends server's public key. So Alice here can then encrypt the shared secret that has been generated before using Bob's public key. So Bob's public key here. Then encrypted master key will arrive at the Bob side. And because Bob is the only one holding the Bob's private key, therefore Bob can restore the master key from ENS. And that's how Bob and Alice establishes the shared secret key. So in this case, you see Alice is the one generating the secret key. And from then on, all the messages are encrypted using the master secret key. And that's how TLS worked. All right. So there are actually quite a few questions here because I'm pretty sure that you guys have not yet taken 密码学 encryptions. So that's the magic of the public-private key system. If you encode something with the public key, you can decrypt it with the private key of the person. Okay. So if it's still not very clear, ask me again. I can probably look up some reference that explains the public-private key system a little bit better. So I hope that the video is reasonably easy to understand how TLS work. And TLS uses both systems, the traditional one-key system as well as the public-private key system. The public-private key system is used to establish the secret key, the traditional key. But later on, when you're exchanging data, both ends use the same key, that master key there, to do encryption. All right, and now we move on to 2.2. Finally, right, we know that the basic design components, there are 4 of them, to do application design. The first example we'll be looking at is HTTP. So HTTP is the application layer protocol for the World Wide Web. Let's review the basic first.
Web and HTTP. Let's do a quick review. Web is essentially a bunch of these web pages interconnected. So each web page consists of a number of objects. The base object is typically a HTML file. And then in each file embedded are several referenced objects. And these objects could be another HTML file, could be a JPEG image, could be an applet or a script or an audio file. Each object on the internet, on the web, is addressed by the URL. So this is an example of the URL. There are three parts: the host name, and the path, and the file name. Okay. And the HTTP protocol there to support the web application runs in the client-server model. So the client here are essentially the browsers. The browsers is essentially requesting for web objects and then in turn receiving web objects, of course, using the HTTP protocol. Now another task the browser does is displaying the web objects. Just to clarify, passing of these messages and web object is the HTTP protocol's job, but displaying web object is actually something else's job. It's the HTML interpreter's job. Yeah, so HTML interpreter is not quite the HTTP protocol. So you see here, a browser, that program there is a combination of the HTTP protocol client side and an HTML interpreter. So this interpreter is to interpret the HTML page because there are some markups around. Based on the markup, the interpreter will know how to display a web object so that it appears properly and nicely. Now the server, web server. Very few of you guys have experience building your web server, I suppose. Yeah, so in this example we see Apache, I think, is still the most used server, but this guy here is catching up, and Nginx. Both of these servers are implemented using C and C++ socket. All right. So the web server implements server side of the HTTP protocol. So what it does is to receive requests and send back response. So that's the exact opposite of the client. It's to receive objects and send requests. So let's see the exchange. So this client up here, sending HTTP requests and then receiving the HTTP response, and containing the HTTP response is the web object. Similarly, if it's a phone, yeah, Safari sending HTTP request and server sends back an object and Safari renders and displays the object. Alright, so that's HTTP, Hypertext Transfer Protocol, HTTP. And HTTP runs on top of this transport layer protocol, TCP. And the whole process is actually this. First, tries to establish a TCP connection between the web server and the web client, and then sends the HTTP messages. So before the client and the server sends HTTP messages, the client and the server sends TCP messages first. So starting from the client, initiating a TCP connection. Now, if this is a web server sitting on the default port, it's going to be port 80. And then server would accept the TCP connection, inform the client, and then client can begin sending the HTTP request. And the server sends back HTTP response. When everything is done, the TCP connection will be closed. Know that HTTP, as you see, very simple, request response. In fact, each of these requests is treated as brand new. It's very fresh. That means what the server is doing there is to not record anything about the client. So there's no information about the past client requests. Okay? And we call this type of a service a stateless service. So on the server side, there's no requirement of storing anything about the client. So this is really nice because the server does not require a lot of memory space for these information. Right? Yeah, protocols that maintain states can be complex. So this is the other extreme. You might need to maintain the past history, which can be long. And you might need to maintain history for multiple clients. How about that? That's a lot of burden in terms of a memory space requirement. And besides the service load, the memory requirement, what if the server and client each crash while the other continues to run? Then the states on the two sides might be inconsistent, and they will have to resolve the conflict somehow. That's the worst, right? So should you trust the client or should you trust the server? This is one of the classic car problems, all right?
So that was a quick review. Let's move on to talk about connection modes. So HTTP, as you just heard, right? So we can probably see the 4 design components, the architecture or the communication model. What kind of model is it using? Client server or P2P? So obviously client server, right? We see also that it's using a socket at port number 80. What is the 3rd design component? I actually don't recall it. Oh, the message formats, right? So we see that they are sending request message and response message, right? We have not yet talked about the definition, the format, syntax, and semantics. It's actually coming next, okay? But the 4th is what? What transport layer protocol does HTTP use? You see keyword already, TCP. So in a way that in many of these applications we'll cover next, okay, as examples, we try to identify what architecture, what communication model they use, what port number, right, which kind of socket they use, is it TCP or UDP, and oftentimes we see that there are also definitions of the messages they exchange. But in HTTP, the communication model is not as straightforward. Client server to crash. I see. It's a very good question. I think this is very timely. Yaqing or Jessica, in reality on internet, okay, my machine crashes from time to time. As you saw in the video, we just showed, Polly's camera just crashed, so that Polly was like sitting pretty there, but the mouse is not moving and there's no facial expression. Okay, so these computers on the internet crashes all the time. Okay, but not quite as frequent as we expect though. But in case they crash, you will see that in stateful protocols, the states on the server or the states on the client, one of them being crashed will not be able to keep track of what's going on, but the other end continues to update. So the data they have will go out of sync. Okay, so that's the trouble that the stateful protocols will have. It's a little bit convenient to have the stateful protocol because it tracks your history. So it might give you preferences and it might remember things you do so they can fill in what you might want to do next. HTTP is designed to be very simple so that we don't have to worry about implementing additional mechanism, so that it's a little bit more resilient to crashes, okay, of the machines on the internet. I hope that addressed the question a little bit more. It might be a little bit hard for you to imagine that the server might crash. Client program might also crash. HTTP, it doesn't just communicate in very straightforward request for a web page and then respond web pages. There are actually multiple ways of establishing the connection or multiple ways of doing the communication, even though it's still client server. So the next video is the core, one of the core content today. The video is a little bit long, but it's very key because there's going to be a quiz following that.
HTTP connections. There are actually 3 flavors of HTTP connections: non-persistent HTTP, persistent HTTP, and third, persistent HTTP plus pipelining. Alright, so let's start from the most basic, the oldest flavor, non-persistent HTTP. This is implemented in the pioneer versions of HTTP, let me call it that way. In that, you send one object per TCP connection. So the clients and the server sets up a TCP connection, and then you send one HTTP request, you get one web object, and then you close the connection right after that. So to download multiple objects, you need to create multiple connections one after another sequentially. Now in persistent HTTP, the main idea is, well, why do we keep opening TCP connections and closing them? Why don't we just reuse the TCP connection we have started in the first place? So in persistent HTTP, client and server establish the TCP connection, and then first web object exchange, second web object request, and the object response exchange, and so on and so forth. So one single connection to send all the objects. All right. Now, the basic persistent HTTP mode works more like that. So you have one exchange to establish TCP connection, and then it's just object 1 and object 2. And then object 3. Okay. But the thing is this. When we establish the TCP connection and sending out the first request for object 1, really, before the object 1 is being transmitted back, you see, client over here, it needs only this amount of time to send the request message, right? Client is immediately left idle right after that. So why don't we send the second object's request, the third object's request, and the fourth object's request subsequently and immediately? That way, you just need another exchange like this and, just a few more transmission time. Then we're done with everything. Unlike here, for each object, you need this much time, and the second object would wait this much time, and the third object waits even more time. Okay, so this here is the persistent HTTP plus pipelining. Nowadays, when people say persistent HTTP, the implication is that, hey, it's persistent HTTP with pipelining. And by the way, this is HTTP, the 0.9 version. And persistent HTTP without pipelining, that's the HTTP 1.0 version. And the one with the pipelining is the HTTP 1.1 version. All right. Now let's go through the animation for the very standard non-persistent HTTP protocol's behavior. Let's suppose we are looking for this object here. So the URL contains the host name, the path, and the file name. And let's see that this base file here contains 10 reference objects. So there are 10 images embedded. Step number 1, the TCP establishment. Client here initiates connection request. Server sitting at this location at port 80 will accept the connection and then send back a, yeah, sure, open it message. Second exchange is the client sending the request message. All right, so in the message, embedded is the URL. All right, so that's going to go through the socket, yeah, and URL right there in the message. Server will receive the message and sees the URL, finds the path, finds the file name, and therefore extracting content and generate the response message. And that response message is shoved again through the socket back to the client. Now, immediately after the response is sent, the server closes the TCP connection. HTTP client here receives the response, parse the HTML file and displays it. And in that process, it's discovered that there are 10 more reference objects to download. And the client then will repeat step 1 to 5 again and again and again, 10 times until all 10 objects are downloaded. And the time to do that is pretty long. Let's try to count the amount of time to complete the entire download. And we call that the time to download an entire page being the response time. Before calculating it, let's define this term. RTT, which stands for round trip time. It is the time for a small packet goes out to the other end and comes back, out and back. So it's a round trip in a sense. So client over here, server over here, to initiate a TCP connection, the connection request go, connection established, granted messages come, that's 1 round trip time, right? So 1 round trip time for initiating the TCP connection. And it's another round trip time to send HTTP request and receiving the HTTP response. So this part is 1 round trip time. But the dark, thick square here, this is the time it takes to transmit the file. Okay. So when the object is very small, this is very narrow. When the object is large, this could also be quite wide. So we fill it up. Yeah. So the object itself could be big. The transmission time can be long. So the shadow part is the file transmission time. So the response time to download just 1 object using non-persistent HTTP is 2 round trip time. 1 here, 2 here, and then the file transmission time. Now we can try to account the response time for that page we were loading, the something.edu, the object there. So we have the base and then 10 more objects. So altogether 11 objects. If we're running the non-persistent HTTP connection, then we have 2 round trip time plus the transmission time for object number 1, the base object. For each of the 10 objects, we do more. Okay, so the transmission time might vary a little bit from object to object, but round trip times remain the same. Right, so there are 10 of these. So 22 round trip time. So 10 of these plus this one over here, the base. And yeah, the sum of the TX. Okay, and depending on which object it is for OI. All right. Now, but for persistent HTTP, the server is going to leave the connection open after sending response. So subsequent HTTP messages between the client and server will be sent over the open connection. Client can send requests, as I said, right? Persistent HTTP without further clarification, it's the persistent HTTP with pipelining. So the client here will send all the 10 requests as soon as possible. Okay. So in the end, It's just one round trip time plus the transmission time of all these objects. So altogether, just 2 round trip time. First is to establish the connection. Second is to download the first object. Okay. Third is to download all the rest of the 10 objects. So it should be 3 round trip time plus the transmission time required to send all these objects. So 22 versus 3. Big win over here, right? Yeah. So this is in HTTP version 1.1, the most up-to-date version.
All right, so allow me to add a little bit to that. So that 3 round trip time for the persistent connection HTTP with pipelining is actually the worst case. Because if you think about it, TCP connection establishment, and then, downloading the first object, right? Because the base web page, as it arrives, we will know that what are the reference objects already. Okay. So one can potentially finish just a little bit more than 1 round trip time downloading all the reference objects. But that's the best case. The worst case can be that, hey, the reference objects are all at the end of the base HTML. In that case, it could take up to 3 round trip times, you see? So earlier when I'm illustrating, so it could take only 2 round trip times plus just a little. That's the best case. And that example I just showed there, 3 round trip times, the worst case. Okay, so between 2 and 3 round trip times essentially. And that takes us to quiz number 8. And when quiz number 8 completes, maybe during the break, we can come back to the questions. There are several questions. I think I type up the answers. Hope that they're clear. But let's move on to quiz 8 first. It's quite straightforward, but you need to think about it. Could you tell the time in units of round trip time to download a web page that has 1 base HTML and 5 reference objects? And let's just ignore the transmission time to keep it simple. All right. Q1 is how much time that will be using a non-persistent HTTP connection mode. Q2, if you're using the persistent HTTP mode, okay, how many round trip times? Q3, persistent HTTP without pipelining. How about that? And non-persistent HTTP, but with parallel connections. So one of the tricks some of the web browsers do are, instead of doing persistent connection, what they do is once we download the base HTML, discovering all the reference objects, instead of having 1 persistent connection, they open up parallel connections and go out fetch all the rest of the reference objects at the same time. Okay, how much time would that cost to get all the reference objects in, including the base HTML? Okay, so let's go ahead and start. Okay, hey guys, this is a long question. So for the long questions later on, I would not actually count if you come in and answer the quiz very fast, because oftentimes I see you guys投降first, and then there are no answers. Okay, so why don't we take time with the long questions? There'll be short questions. You guys will know. Then hey, fast answers get extra points. There'll be 2 more today that are short, but this one is long. Think about what I just said and make sure that you get everything clear. So you do have 5 minutes. Let's go ahead and start thinking.
一杯咖啡，浓一点。
一杯咖啡，淡一点。
Sorry, commercials cutting. Yeah, let me see if I can bypass the commercial. Yeah, and have the, there we go. Okay, time's up. Turned out that the quiz is too hard, too challenging. Yeah, I guess you guys are still busy recalling, hey, exactly what's going on there. But it's okay. This is a long question, so take your time. But let's, in the meantime, move on to the next segment. This is coming to the fourth design component, the request message. Defining the message format. Oh, wow, okay, good. We actually have some solutions. Okay, so we'll come back to quiz number 8 a little bit later. And let's move on to look at the message formats. So first is the request message, and second, the response message. As I just said, you see also, oopsie, the sides are not. Okay. So you see that there are two kinds of messages, request and response. Okay. One key characteristic of all these messages that we see in application layer protocols is this. They are human readable. So ASCII is a code used very often to represent characters, okay? Human readable characters, English characters, Chinese characters, French characters, Latin characters. So you see that the HTTP request messages as well as response messages, it's very readable. you might be able to understand quite a bit of what the client is trying to communicate to the server, as well as server to client, pretty well by intersecting these messages and looking into the content. Okay, so here below is an example. It starts with get space index HTML. Okay. Now, before I ask you to try to exercise and guess what might be in this HTTP request, let me give you a very short course, 2 minutes course of the syntax of request message. Let's take a closer look at the syntax of HTTP request message. First is the request line. It's only a single line, 3 tokens, separated by 2 spaces, one over here and one over here. First token indicates the command the client is issuing to the server. So get here is the most classic command. Second token here indicates which object the client is wishing to download. So here you see the path and the file name of the object. Third token is very straightforward. It's simply telling the server the version of the HTTP protocol the client is implementing. Now, header lines. Syntax is also quite straightforward. Column in the middle. Before the column, this is called the attribute or the field name. And whatever comes after the column is the value of the attribute or the value of the field name. All right, so user agent is a well-defined attribute in HTTP. It indicates what implementation the browser is and the version of it. So user agent indicating the meaning being user is using a browsing agent called Firefox, and it's version 3.6.10 of Firefox. Okay, similarly, okay, keep alive, also a predefined attribute. And the value 115 is saying that let's keep the connection alive for 115 seconds if there are no messages being sent. Connection indicates the type of connection the client is wishing to establish. It's the keep alive kind of connection. And so you see the syntax and a little bit of semantics of HTTP requests. All right, and this is quiz 9. It's a short question, okay, knowing a little bit what the syntax is. So this is what you're seeing in the box is the HTTP request being intercepted, okay, and from it you know that it's an HTTP GET message. This means that the client is asking for a web object, a web file. Okay, and you can probably see it in the message exactly what object is it's requesting. So Q1 here is to ask what is the URL, okay, of the document, okay, being requested by the client, okay, and tell why do you think so. Q2, is it a non-persistent or a persistent connection mode that this connection is, okay, getting the web object, and how did you tell? And you know what? With this quiz out, we take a break, 10 minutes. So you guys will have time to think through quiz 8 and quiz 9. And you know what? Let's go back to the flight attendant mode. There. The flying mode. And where's my Eva Air landing music? There we go. let's come back to quiz 9 first. So I guess it is indeed straightforward, isn't it? I see many teams have answered quiz 9. So you guys find that the request must be going to an URL that looks like the host is gaia.cs.umass.edu because you see it in the host part of the HTTP request message. And you find the path and the file name from the command line, okay, of the message. And then for the connection type, you guys see that in one of the fields in the HTTP request header, it's connection and then keep alive. I think in one of the fields it says keep alive and a specific amount of time, isn't it? Okay, so quiz 9, straightforward. Let's go back to quiz 8 a little bit. Okay. Yeah, I see several students, several teams have started answering. Yeah, for quiz 1, it's pretty short. We have 6 files. So each take 2 round trip time, 12, very clear. And persistent connection with pipelining, the worst time, 3 round trip time, right? Because you need 1 round trip time to establish TCP connection, 1 round trip time to get the base object so you know what are the reference objects. And then just 1 round trip time in the worst case to get all the reference objects in. So that was 3 round trip time. I think all of you get that right. Yeah. Now, what about persistent connection without pipelining? So there was an intermediate version of all the connection mode, right? So in that case, we don't have pipelining. That means 1 round trip time for TCP connection, 1 round trip time for the base object. So now we have all the reference objects. But we cannot do pipelining. So for each of these 5 reference objects, we need 1 round trip time, 1 round trip time to get each one of them. And there are 5, so 5 round trip times plus 2 round trip times for the TCP connection setup for the base object. So that'll be 7. Yeah, I think many of you get it right. Okay, Mao, quick action there. Okay, and I guess the delay to you, Mao, is also very short. And what about the last one, parallel connection? Yeah, we didn't spend much time talking about that. You guys are really good. You guys' actions online are much faster than Polly does. Okay, so when I was playing Maple Story, I'm always the slowest one. All right, so 4 round trip times and 3 round trip times. You know what? You guys are both correct. Because it depends on how many parallel connections allowed by the operating system as well. The way having parallel connection, so the reason that I asked this Q4 is because before we have the newer version, persistent connection. Is there a difference between base and objects when transmit? Each of them is a file. Except that you need to have the base HTML downloaded in order to know where the reference objects are and exactly the path and the file name. Okay, Yuxiang, you are asking the right question because Polly is trying to explain. The parallel connection option, it's implemented in many browsers, even still today. Okay, but it was an alternative to shorten the response time when there's no HTTP persistent connection mode. So it was the original non-persistent connection mode. In that case, you see the response time very long, right? For one page with 5 reference objects. So by that 5 reference object, I meant additional objects that you use you use these hyperlinks to refer to other pages outside, or additional images. Okay, you want to include in the page, or soundtrack you want to include in the page. So these are called the reference objects. So when you have a web page that has additional images, additional soundtracks, what's going on there is that the browser, after knowing the exact URL of the images and soundtrack, they will need to issue additional web requests, HTTP requests. Okay, that's why you have additional round trip time. So when there's no persistent connection mode, 1 round trip time to establish TC connection, 1 round trip time to get the base object, and then what? Start another TCP connection to get the first reference object, right? Another TCP connection to get the second reference object. But this is taking so long. So what the browsers does is after getting the base object, all these 5 objects, they start parallel connections to get all 5 of them at one time. Okay. But you know what? Many of the web browsers, they also try to be a little bit conservative because, hey, there could be like 100 reference objects in that base HTML. So they often limit it to 4 parallel connections maximum. So for 5 reference objects, you do use 1 round trip time to get 4 first, and another round trip time to get that one more. Okay, so 1, 2, 3, 4 round trip times. Okay, so many of you have guessed it right. Sorry for being very tricky here, asking how long it's gonna take to run a parallel connection, non-persistent but parallel connection mode. But I guess Mao, you are actually right in case you allow 5 parallel connections. So 3, 4, both are right. In case that we allow only 2 maximum parallel connections, how long? Yeah, 3 additional round trip time. So it will be 5 RTTs. Okay, I hope that's clear. Okay. There's a question from Liang Yu. Is there a difference between base HTML and OBJs when transmit? Yes, I think Liang Yu, your intuition is right. The base object, you need to have it first before you know where the reference objects are. So you can start fetching the reference objects. Oh, I think that's a good question. I might be wrong in the video earlier. Yeah, so you need to do 1 round trip time and then the reference objects begin to show. So the best case will still be very close to 3 round trip time instead of 2. Okay, Liang Yu, that's a key question. Okay, so, Polly made a big mistake in the video. Okay, I have to correct that video. So very good question there, Liang Yu. Bonus participation points for you. All right, and then we move on. Okay, but before we move on, there's just another short video explaining in the command line of the request message. Get is not the only command. There are actually more, and as the versions evolve, there are more and more. Okay, let's take a look.
And the last slide about HTTP requests here is quite straightforward. What it says is to tell you again what are the comments, okay, possible in HTTP request line. In version 1.0, we see get, we see post, we see head again. But this is all that HTTP 1.0 supports. In HTTP 1.1, we extend the comment options from the 3 classic ones to add 2 more, put and delete. Okay, let's go through these 3 other comments. First, the head comment. So this is usually for a web client to send sort of initial HTTP request to the server, and server will send some response back, but only to tell the status of the server or the specifications of the web server, and leave the actual web object the client is asking for out of the response, so that the response is very short. And what's contained in the response messages are just all the essentials, like, what is the version of the web server program you're running over there? what is your IP address, what is the time date, what is the time date, the object that the client is asking for being modified last. Okay, things like that, the essentials about the server, about the object, so that when the client receives a response like that, the client can plan a little bit better ahead of time how the client does the requesting. Sometimes when the file is really large, the client might try to dissect and then do the requesting slightly different. And put here, this one is actually quite forward, just to upload the file in the entity body of the HTTP request to the server, right? So in that request, we also specify which path in the server we want to upload this file to. Okay, so it's working pretty much like the FTP. If you recall FileZilla, you are dragging a file to the server, right? So it's uploading a file to a specific path on the server side. So put here implements file upload. Delete, deleting a file. So FileZilla also allow you to do this. So essentially, HTTP 1.1 is to extend the original HTTP to include all the file uploading, downloading services, because the original HTTP only does file downloading, not quite the uploading. Now, when HTTP 1.1 is available, FTP protocol quickly loses its popularity. Okay? And that's why we rarely use FTP these days, because HTTP, the web browsers can do all these for you. All right, so this is HTTP request.
Okay, so I think I said something wrong again. So you guys are perfectly right. Mao, we got it wrong. Sorry. In fact, this is non-persistent connection. So we need one TCP to set up all the parallel connections and then send the reference objects once. So I guess all the other teams ended up having 4 round-trip time. They are actually assuming that all the 5 reference objects are going in parallel at the same time. Okay, so Mao, we missed that TCP connection setup time. Okay, so guys, you guys are good. And I like that you guys add explanations to it because as I read, Wei Yo here, adding to what Mao was saying, it's very clear. And I think some of you, also say 1 round trip for the base object, right? And the connection will be closed because it's a non-persistent connection, HTTP. So we need to start TCP connections for all the 5 parallel connections at once. Okay. Now, if we limit the number of parallel connections to 4, so that's 2 more, so 6 round-trip times. Okay. If we limit parallel connections to 2, 1 round-trip time for the base, 1 round-trip time for the first 2, another round-trip time for the second 2, and another round-trip time for the remaining 1. Okay, so wow, another 2 round-trip time for each of the 2 sets of parallels. So 2, 2, 2, 2 will be 8, right? So 2, 4, 6, 8. Mm-hmm. All right, so good, very good discussion. I guess finally we get the response time, the calculation of it for all different modes, right? And then we are ready to move on to the response message. Okay, it's actually very similar to the request message. Again, it's readable. Now, instead of going into the syntax first this time, let's go to a quiz first. Okay, so quiz 10. So this is the response message. Okay, can you tell? Okay, whether the server is saying the document or the object the client is asking for is found successfully? And how many bytes is in the document? And what are the first 5 characters of the document being returned? Okay, and you know what? I've already seen some students responding. Okay, so you guys are really fast. let's go to Slack here. Okay, so team 13 here is saying yes, because there's a line saying 200 okay, so you guess that it's coming correctly. And how large is the file? Okay, let's see if, yeah, this shows. Oh, you see something like content length, right? 3A74, okay. And the first 5 characters, okay, there you are. First 5 characters, let me see. Okay, so there's an empty line here, and then following must be the data, which is the web page. So it starts from a less than sign and an exclamation sign, and then DOC type. Yeah, so indeed, the first 5 characters are those. Okay, Team 1, Yuxiang. Team 7, Jieming. Very good. Okay. Yeah, so why don't we take a look into the syntax of response?
Now, finally, the HTTP response message. Okay, the second type of messages defined in the HTTP protocol. You see here, generally, 3 parts. First, the status line. Second, the header lines. And the third, the data. So the entity body, so to speak, from here and down. Okay, and these are very similar to the header lines we see in request message. Each line, you see attribute and the value. Attribute and the value. Status line. 1, 2, 3. Again, 3 components. Let's go through each one of them as well in a bit more detail. In status line, first here, familiar. So the version of HTTP the server is implementing is the first component in the status line. Second, this is the status code. Okay. So in HTTP, it defines quite a number of these status codes. Each of these indicate a different condition. Some more related to the server, some more related to the object being requested. And for each of these status code, there's a status word being shown as well. That's the third component in the status line. So 200 here indicates okay, meaning the HTTP server is working well and the object you're looking for has been found, and it's going to come here in the body entity. Now, second part, the header lines, we see date. Yep, this is the date, time, the request is being filled, and this response is being generated. The server, this is an Apache server, version 2.0.52. Yep, Apache is one of the most commonly used web server implementation. Yeah, I think you heard about the other one, Nginx. So Nginx is certainly rising. Okay, it's not quite yet the most popular one. Well, let me clarify. By popularity, I meant the number of machines running a specific version of web servers. So Apache is still the most used web server. But if you count only the number of downloads recently, it might be Nginx. That's why you see I said that it's actually rising. So I think maybe in just a couple months there will be more Nginx server than Apache servers. Last modifier, so this is to indicate when is the object you're downloading last modified. Oh, okay, it's really long time ago. All right, e-tag. What is this? This is actually, hey, for each version, okay, of the object that you are downloading, there comes also with a version number. So e-tag there is to indicate the version number. Nowadays, as you see, the HTTP protocol is not used only for downloading purpose. It can also be used for uploading. If there are multiple users there using different web browsers trying to upload the file, for example, Poly and Caleb, the TA, tries to upload and override the grades Excel file, then you might have a consistency problem there. So the number here is to break time, to make sure that a newer version does not override an older version or something like that, to resolve conflicts, so to speak. And accept range. Yeah, yep. So, you know what? Earlier when I mentioned the head comment in the HTTP request message, right? So when you send such a comment in the HTTP request message, the server responds with only the status line with the header lines, but without the data. So server there can actually tell the client, you know what, I'm a server that allows you to request content in terms of bytes. So the client there seeing this can then send the request more officially, instead of using the head command, using the real get command, and request to download byte 0 to maybe 1023 or byte 0 to byte 100. Okay, so you could do a range request in a way. And the server's next header line, content length. This is to indicate the size of the file or the size of the object that you're downloading. So you see the file size of the object is one critical parameter. Okay? If you're implementing a web server, you need to know a way to find out what the file size is or the object size is. Okay, the size is a bit messy. Let me clear the markups. Keep alive. Oh, good. This web server implements persistent connection. Okay, and so it indicates timeout interval is 10 and maximum 10 requests. So this is a persistent connection, but in the connection, it only accepts up to 100 requests. All right, so if it's more than 100, then you will force close. The server will force close the connection. So connection, keep alive. Content type, yeah, just like the client size header line we see. Yeah, the client accepts content of a certain format. Here, okay, this is to indicate the object the client is asking for, which format it is. And we see this is text-based HTML file and it's coded in ISO AA59. Right? And empty line, indicating this is the end of the header lines. Right after the empty line, the data goes here. If it's an HTML file, then hey, text starting from here. Okay, the first file. So this is an example of HTTP response message. You see the structure is very much like the HTTP request messages. Next is just to share a bit more. HTTP response message is status code. We've seen earlier in the example 200 OK. This is saying request is successful, object is already embedded. 301, that means the server is saying the object is moved to a new location specified later in this message. So sometimes when you run into a message like this, you see, oh, click here. That's going to take you somewhere else. It's a redirecting link. If you see status code 400, that means, ooh, your HTTP request format is not quite correct. bad request. 404, that means the object you're asking for is not found. 505, HTTP version not supported. So in case you're using a very old browser, or if you are contacting a server that's very old, and yet your browser is implementing something newer, then you might not be able to communicate. The server is going to tell you this. Sorry, 505.
All right. So you guys are asking questions that you might see that they will be answered. For example, Boris, how do you get the messages? I'm going to show you a demo next. Version between HTTP and HTTP 1 something versus HTTP 2. It's a very good question. So you see here on our Google Me window, I'm showing you the difference. So HTTP 2 is version 2. So that effort is mainly driven by Google. They want to speed up, again, shorten the response time. So what they want to do is, instead of sending ASCII codes, usually that in ASCII code it takes more time, more bits, therefore more time. So they try to encapsulate all these text messages and save them in binary formats somehow. So that would shorten the response time. Okay, so that is called SPDY, SPDY. What else? Okay, so Minghong was asking, is 404 code status code? Yes, it is. Okay, it means not found, file object not found. Okay, so let's go ahead and take a look at the demo.
So what I will show you in the demo coming next is to do this. Telnet to the favorite web server here, and we're going to use this machine here that the textbook author has set up for us. So we'll telnet to gaia.cs.umass.edu at port 80. Okay, what it does is to open the TCP connection to port 80, where there's a server already running, a web server already running. And anything typed in will be sent to port 80 at this guy. Okay. So Telnet is a remote logging application, just like SSH or RSH, if you know what it is. It's another remote logging command for native Unix users. All right, so Telnet is very old. Many operating systems probably doesn't support it anymore. But I've already installed it on my Mac, so we're going to show that in a little bit. Now, once we telnet to the web server, and we'll type up some things. Okay, let's try typing this. Get path name and file name as the argument for the get command, and then the version of the web browser. So we'll be pretending that the telnet here is a HTTP 1.1 client. And host gaia.cs.umass.edu. Right? So header line. So essentially we are trying to do a human web browser. Okay, by typing online right here an HTTP request message. So once we are done with this, we hit return. Okay, and then we hit return again. Needs to have a what? A \r\n here in order to complete the HTTP request. All right, so the whole thing is going to be like this. And yeah, we'll see what pops up in return, what the server there at umass.edu sends back. Okay, let's not sniff the traffic. Let's just look at the response coming out of the telnet program. All right, so let's switch to the demo mode. All right, let's telnet to gaia.cs.umass.edu at port 80. All right, connect it to gaia.cs.umass.edu. Now let's pretend to be a web browser. Get. Oh, wow, that's pretty long. The path in the file, pretty long. Let's copy it from the sides. And over here in print. All right. And then host. poly.ntu.edu. How about that? All right. And one more empty line to indicate this is the end of the header lines. There we go. Wow, it's returning a lot of things. Scroll back, and scroll back. Wow, very long in fact. But it looks like it's an HTML file, right? It's an HTML file. This is a hyperlink to an text HTML file. Okay, let me scroll a bit faster. I don't know how long this is. Oh, there we are. Yeah, so we typed up this line here. Okay, and we also say we are host poly.ntu.edu.tw and an empty line and then return again. The whole message gets out to the web server at gaia.cs.umass.edu and the web server returns this http://11 to the 200, okay. And header lines, number 1, the date. Header line number 2, the server. Oh, it's an Apache server. X power by PHP, I see. Content length, content types. And hey, empty line to indicate this is the end of the header lines. And starting from here, the real body. Okay. So we get the output of calling this PHP query at this path. Let's see, interactive problems, computer networking, a top-down approach. Oh, okay. So this looks like the main page of all these interactive exercises that we see every now and then on the slides. All right. So there, essentially very text-based interaction between the client and the server. As human beings, we could also do it right here, right now, online as a web browser. All right. Good. And I think let me just go back a little bit here. You see here, 200 is a very classic example of the syntax defined in an application layer protocol. In HTTP, to be exact, 200 is to indicate OK. So OK here is just to say it explicitly, the semantic of 200. Right? So that concludes the messages format, semantics and syntax of HTTP.
All right, so finally we've done with HTTP. There are two more subjects, cookie and cache. But these are additional functionalities later on people added to HTTP. Okay. Before we move on, let me come back to quiz number 8 again. So team A, very interesting. So the students are ahead of us. The textbook says that the number of parallel connections is usually 5 to 10. Yeah, that's nice. Hey, the reason that I say 4 is because when I was checking last time, it was 4. But I checked again. You see here, Google Chrome, the default was 6. So such as what the textbook said. But let's see what Safari uses as default. It turned out that the max number of simultaneous connections or parallel connections Safari can be different. 6 for Mac OS and 4 for iOS. Okay, so I guess these numbers are changing all the time. I think in some browsers, one can actually set up even more than 10. So it's user determinable. But the default, I guess, it's pretty much ballpark in 5 to 10. Okay, good to know. And now we move to the additional improvements to HTTP. So the first thing is called cookie. Okay, let's check out the mechanism.
Cookies, yeah. Many websites these days will try to prompt you to set up cookies before they allow you to visit the website further. So it's very, very relevant to our everyday life. Let's see how it works. Okay. First thing is, the cookie setup process is always initiated from the website. So meaning from the web server that your web browser is requesting objects from. So web server there is going to send a message to the web browser carrying a special header line. Okay, it's the cookie setup special line. And the web browser there, upon receiving such a message, it's going to generate, okay, a corresponding message if you click OK to insert cookie. And that message is going to carry, again, a special header line saying cookie OK. All right, so exchange of messages between cookie setter and cookie allower. Now, when you say, OK, I will allow setting of the cookie, your browser is going to add an entry to the special cookie file on your local disk. Okay. So that is exactly what's expressed here in the special cookie setup line. And when the server receives the message allowing cookies, server would then add a special entry as well to the backend database. And that entry set up here and here will actually map to each other, allowing the server to identify who you are and when have you visited the website last time. Okay. Let's use an example to explain. It will work slightly better. Let's say Susan always accesses internet from her PC. And she's visiting a specific e-commerce site the first time. In the initial HTTP request, okay, that arriving at the server, the site will then create a unique ID, okay, and that will be an entry being added to the backend database. Right? So that ID is going to be carried, okay, in the message the site sends back to Susan. So that's going to be set cookie and then the number created here. All right. So local hard disk you have there, or Susan has there, will have that entry, okay, set up in the cookie file. So this will go back to the server, okay, carrying also that special ID that Susan has already allowed to set up. And then at this point in time, the server would finally enter the entry to the backend database. So that's the way it works. Let me illustrate, okay, and so that you know clearly what's going on. Client, server, or Susan, Amazon.com. Okay. Now, at the client side, you have this special cookie file, and it's managed by the web browser. And you might have clicked OK to eBay. So eBay has already set up a cookie entry carrying unique ID 8734. Server here has a local disk as well. It's maintained more as a backend database instead of just a simple file. Right? So, but when you visit the website Amazon.com the first time, you send an HTTP request message. Now, of course, you have not yet been in Amazon before, so there's no entry for the Amazon website. Okay, so in your initial HTTP request message, there's not going to be any cookie special header lines. All right. So when Amazon.com here receives HTTP request, of course, it will try to grab the objects that you're looking for and try to generate the HTTP response with it. But in the meantime, it will be creating an ID, okay, for this particular user, okay, and add that to the database. And in the response, it carries the web object that you're looking for, but it also carries the special header line, the set cookie line. Okay? And hey, see the ID created is carried over through the HTTP response message back to the user. So, web browser here sets up one extra entry saying, hey, for Amazon, the website, use ID 1678. So for the subsequent visit, subsequent browsing, all the HTTP request messages is going to carry the cookie OK and I am a user 167A header line, right? So here the server, of course, will be generating the web objects, generating the HTTP response message that you're requesting with the request message. So response message. But the response message might also contain additional content. Okay, server there could be seeing your browsing history a couple clicks back and discover that, hey, you might be looking for a specific item. Okay, and then recommend potentially items you'll be interested. Okay, so that might also be part of the response messages. So showing the items you are looking into buying as well as related products. Okay, so for example, if you are looking to purchase a phone, then the website might be recommending a phone case, okay, or a number of phone cases. So what's amazing there is 1 week later, okay, when you come back and try to purchase something from Amazon again, the first request message you'll be sending will already be carrying the cookie entry. Okay, so once you have it set up locally on your cache file, on your cookie file, for all the subsequent HTTP requests, it's going to by default carrying the cookies. Amazon here will know, yeah. So over time, the server will know probably your profession, probably your income level, things like that. Okay, so that's why it gives people a certain creep about setting up cookies, and you might be warned, be careful about setting up cookies there. Now let's discuss cookies a bit more. We're going to talk about the trade-offs of using cookies. First, the cookies, from a business perspective, from a website's perspective, is actually quite convenient. So you see, you can authorize the users quite easily, okay, by looking at the ID in the cookie header line. Tracking the shopping carts as long as the ID is the same, right? This is items purchased from the same user. You can recommend items so that the users will go, wow, cool, that is exactly what I was looking for next, right? If the user is purchasing a phone and the website suggests purchasing of a phone case. Yeah, and browsing emails, yeah, you will not want to try to log in and type up password again and again. You want to be able to maintain that email reading session, email sending session over time and log in just once. How? Very nicely through the cookie line in the HTTP request. Okay, quite convenient. Okay, otherwise, you guys, including Polly, when I read my Gmail, I have to log in again and again and again. There's no way we could live like that, right? So, convenience. But on the downside, those websites will be able to learn a lot about you. So you store emails, that's pretty much your personal life. You store your purchases there, that's pretty much also your personal life. Okay, so over a long time, you can imagine Google, Amazon, Facebook, all these major websites, they know a hell lot about you. That's why people are freaked out so much about these big sites, okay? Allowing them to set up cookies, allowing them to store information about you, okay? So, downside, privacy. Okay. Now, another perspective is more technical, keeping states. Now you see, hey, there's ID on the local cookie file. There's ID stored at the server side, the backend database. So server and clients are now storing states of each other, about each other. But some of you might go, hey, wait a minute. Didn't we talk about HTTP being a stateless protocol? And what's nice about stateless protocol is that, hey, none of the endpoints need to store anything about each other. Okay? No storage requirement. And you don't have this problem where, hey, if the connection between the client and server is broken, and you might have these inconsistencies in the states they maintain for each other, right? You have to reconcile and resolve conflicts. And that is actually a very, very hard problem, okay? Who do you trust more, the server or the client? Okay, sometimes it's a bit hard to say, okay? So cookies here you're seeing is, in a way, a hacking HTTP such that we can maintain states, because HTTP was not designed at the first place to maintain states. But then now with the cookies, we have this issue potentially between the client's cookie file and the server's backend database. What if, the entry is inconsistent? Then you might have an issue as well. So trade-off in terms of usage, okay, in terms of privacy concern. Trade-off in terms of technical difficulties maintaining the states. All right.
So that's all the time we have for today. So those were cookies. Mindy had a question asking, if you clear the cache file, would we clear the cookies as well? Well, you know what, Mindy, you're asking a very good question because we will talk about cache next week. You'll see that caches and cookies are different things. So cookie, you now know better that they are there to track the users better, okay, the history of the user better. But cache are actually to store copies of the web contents we have visited before. Okay, so slightly different. And yeah, Rocket bumped into the session. Sorry about that. I usually accept them all the time. Yeah, so nowadays, for many websites we are asked whether we will allow them to set cookies. And if we don't look into the detail, we might allow them to see a lot of us. So I don't know. It's really tedious these days. I am also getting tired of selecting what cookies I will allow. If you go to the settings, you will see there are many options. Oh, okay, tell me about it. So Mindy said that I accept them all the time. Shu Quan, I wonder the difference between cookies and cache. It seems, okay, very good question. You know what, Shu Quan, tune in next week. We'll see what caches are. Okay. Could unique ID in cookie file be changed by anyone? You know what? You can try to change that. It'll be interesting. You might be seeing other people's browsing history. So that way the server might mistaken who you are, might be mistaken of who you are and recommending weird things. Ooh, okay, so hey, I don't do that because I don't want to see things that I don't want to see. All right, and guys, you know what? We have already arrived in LA. Hope you enjoyed the ride. I know it's a little bit bumpy in the middle, especially when we're talking about the different connection modes and calculating the response time. But I guess it's not bad at all that there are some confusions, and Polly has the opportunity to clear the confusions. So don't forget your bags and be careful. Okay, watch out for other people's bag along the way out, and enjoy LA. The rest of the time will be office hour. Feel free to join the Google Meet. I'm gonna be around for another hour. So, okay, good. Okay, so Yuxiang has the same question as Shu Quan. Good, so you guys all cannot wait to know what's coming up. So come next Wednesday, you will hear about cash. Oh, Zhonghuan, laughing, good. Yeah, so I might as well do the DOP, okay, till the end. Yeah. How do inconsistency problem be solved? Yeah, it's hard, Yanjun. This is a very good question. Usually you look at the record from both ends, okay, and you try to look to which part the two ends are consistent, okay, and then you see one of the end is more updated than the other end, okay, and usually it depends on the data you are trying to maintain being consistent. Sometimes it's better to abort what the other end sees newer and roll back to the state that is consistent. Because otherwise the server might be forced to add things that might not really happen, because the client end of the data, it can be manipulated by the users. Okay, so for game data, for example, you always roll back so that we always go back to the time when server and client are consistent. Okay, it's a very good question. This is a research problem, in fact. Boris asking where we actually in. Okay, you guys have already landed in LA. I know it's only 2 hours. It usually took us 12, 13 hours to go to LAX. But yeah, this is supersonic ride. Okay. You guys are supposed to exit the plane. Yeah. Go get lunch. I like the music of Deng Yuxian. I love the music as well. It was beautiful. Oh, okay. Thank you, Mindy. Please come fly with Ava Air again. Sorry. Yeah, I miss traveling. Okay, I miss the other half of the family as well. Okay. All right, so let me record the stuff on the chat. Yeah, it's time to get your meal. Okay, so there's no meal served because of COVID-19 on board. All right.